SAC 227 problem number 3, we're supposed to use a graphical method for determining some characteristics of the image formed by a lens. The first thing they want to know is at what distance O is the object from the lens. And go ahead and measure that. This ruler marked off in centimeters. Yeah, with the smallest tick marks actually being that millimeter separation, and as best I can tell, that's 3.90 millimeters or centimeters, and another tenth here because I didn't get the ruler lined up, so I'll call it 3.91 centimeters for O. O equals 3.91 centimeters. That's one of my answers. Then they want to know what's the height of the object. Move that ruler out of the way. I'm going to use this one for measuring the height. And I'm getting, looks like best I can tell, about 0.95 centimeters. So H equals 0.95 centimeters, estimating to the nearest tenth of a millimeter. As I look at it, it looks a little bit taller than that. I'm going to call it 0.96, and that's about as close as I can measure it. And then what is the image distance? Okay, to do that, we got to do our principal ray diagram. Using the graphical method for solving these lens problems, you got to draw a principal ray diagram. You'd be using a ruler. I'm going to try it with some of the drawing tools. We've got one ray comes in parallel to the lens, and when it gets to the plane of the lens, it abruptly changes direction so that it passes through the focal point on the other side, where this is the plane of the lens right here. This object is the plane of the lens. This line, this vertical line, is the plane of the lens, and this is the principal axis of the lens. Okay, so I got principal ray number 1 on there, and then principal ray number 2 is one that extends again from the tip of the arrow representing the object. This one goes straight through the center of the lens and just keeps on going straight through. Looks like I just barely drew this guy long enough. I think I'll try to extend that a little bit. And still got it passing right through the focal point, looks like. And then the last principal lens, let's put arrowheads coming in as well as going out. So get an arrowhead on this line right here. And I think we can see the arrowheads on the other one, but I'll put one more on there. On that side and one more on this side. Arrowhead's an important part of the diagram. And then that last principal ray departs the head of the object, and then when it gets to the plane of the lens, it abruptly changes its direction so that it's coming out horizontally. And at this point we've got all three principal rays. We see that they cross almost at a point. I've actually got 1, 2, 3 points in there. So I got to draw the. I'm going to pick a point roughly in the middle, and I want to make sure that it doesn't jump to another point. I got to get rid of that snap objects to other objects, and then go ahead and draw a line from the midpoint of those 3, which I'm finding to be about right there, to the principal axis, and I need an arrowhead on that. The tail is always right on the principal axis, and the head is at the other end, so I'll put an arrowhead on that, and there's my image. Okay. Now I need, I want the image distance. And we got to measure that. Put the ruler over there. And I got the 0 lined up right there. That was the 0 mark. So I'm at 1, 2, 3, 4, 5, 6, 7, 8, 8.1, just short of 8.2. I'll call it 8.18. So I equals 8.18 centimeters, as closely as I can measure it. So you should expect to be off by up to 2-3 millimeters from what you would get by means of an algebraic calculation, but still in the right ballpark. But with the measurements, 1, 2, 3, 4, 5, 6, 7, 8.18 looks like a reasonable call on that one. And then what else do they want to know? The image height, h prime. Drag this one over for measuring vertical distances. And as far as I can tell, it's here's 1. And that was just a half. So 1 point. It's like a little bit more than 1.9, 1.91, I'll call it. So h prime equals 1.91, and that's centimeters. This ruler is marked off in centimeters. And what's the magnification? The magnification, m, I guess the actual value of h prime is the negative of that, because it's upside down. So the convention is, if it's upside down, you put a minus sign in front of it to signify that it's upside down. I wanted this to be a lowercase I. So I got a minus sign there. For the image position, is positive, in that the convention is, if it's on the opposite side of the lens, from that side of the lens from which the light is coming, from where the object is, then it's a real image, and indeed it is on the opposite side of the lens. So if it's behind the lens is the language that we've been using. So the side of the lens that the object is on is called the front of the lens, and then this side the back of the lens, and hence we're behind the lens in this region. So the magnification, by definition, is equal to h prime divided by h, and that is, in this case, minus 1.91 centimeters, all divided by 0.96 centimeters, and I get, I'm going to have to go ahead and calculate that. So minus 1.91 divided by 0.96, and I get minus 1.99. And we're limited to 2 sig figs here, so I'll call it minus 1. Well, that would be 2.0. Minus 2.0. It rounds off to minus 2.0. So the minus sign means it's upside down, and 2 means it's twice as big. Is it real or virtual? Well, we've got actual light rays converging to a point here. We didn't have to use traceback method to find out where they would cross. So it's real. And it's clearly upside down. It's inverted. And that covers it. That answers all the questions that they asked in SAC 227, problem number 3. Check.